Thank you very much for coming. I'm Adrian. I'm one of the co-founders of Anoma. And really, in a nutshell, Anoma is a unified architecture for full-stack decentralized applications. And today, I'll sort of spend this talk to go over what this means, what intent-centric design means, how this matters, why everyone is currently converging on this kind of architecture, but not in a generalized fashion. Since we had I'll give you a little of background sort of on Anoma and myself and the team, because this is a Cosmos event. So I joined Cosmos or Tendermint in early 2017. I was one of the first core protocol engineers. This is also where I met my two current co-founders. We built up one of the very first proof-of-stake validators for Cosmos called Cryptium Labs. Luckily, we're out of this game, and someone else has to deal with infrastructure. If you're running a validator, you know what I mean. Cool. I'll do a brief historic recap here on sort of the evolutions of protocols that we have seen and how we got to where we are today. So, and I'm using a very different delineation than I think most people use for thinking of evolutions of protocols. So the first generation was Bitcoin and gave us scriptable settlement, right? And with scriptable settlement, we could build cryptocurrencies, we could build things like colored coins, we could build things like Namecoin, which coincidentally actually Namecoin wasn't built on top of Bitcoin, but rather on a fork of the Bitcoin core client. But so back in 2008 until like 2013, people tried to be as expressive as possible within the constraints of scriptable settlement on Bitcoin. As a result of the limitations of scriptable settlement, we eventually got to the second generation, which was programmable settlement. And all of a sudden, we could move away from colored coins and have ERC20s, and we could move away from Namecoin and get ENS. And actually, Vitalik talks about this in the Ethereum white paper, which is sort of the predominant reason why Ethereum came about was in order to overcome the limitations that scriptable settlement offered or had on Bitcoin. The very nice thing, though, is that we not only got the applications that sort of we knew back in the day we wanted to build on Bitcoin and we made them slightly more efficient, we got a whole host of new applications that weren't possible to be built on scriptable settlement. Like we got DAOs, we got NFTs, we for some reason now have soulbound tokens. We got like private voting, we got we got these auction protocols to run the early ICOs and the early fundraisers, right? So something I think no one imagined when Ethereum early on came out, but now we have all these very cool applications that we can build with this. But there are also limitations to programmable settlement because it's not everything that you need. So if you look at sort of some of the modern applications like DEXs, AMMs, NFT marketplaces, like OpenSea, they all work, but again, they work in a clunky fashion. They are very specific trade-offs where, generally speaking, you get at least one centralized Web 2 component in the stack. And so, for example, when you think of OpenSea, right, what does a user do in OpenSea? A user signs a message, sends it to a specific Web 2 server run by the OpenSea company, which then aggregates a bunch of these signed messages, does some compute, then the server does some compute, and then the end result is settled on Ethereum. This is true also when you look at 0x, when you look at CowSwap, it's always this pattern. A user signs a thing, has to send it to a central server does some compute, and then ends up settling, executing the sort of resulting state changes on some other system. I have to say, and because most people use different delineations and scriptable settlement and programmable settlement, we've made a ton of advances on programmable settlement, but I would call them different colors of, like slightly different colored versions of Ethereum, right? We've made advances in proof of stake. We've now have a bunch of scaling solutions using rollups, whether optimistic or zero knowledge. We got advances in privacy. I worked on Tendermint back in the day. Like we have massive advances in consensus with Tendermint, Avalanche, and maybe at some point ETH2 single slot finality, we'll see. But fundamentally, they're all programmable settlement, right? Like what Near offers in comparison to, let's say, Ethereum is like, it's a different color. It's like a slightly faster VM. It's a slightly more sharded VM at this point, but it's still exactly the same application model that's just programmable settlement. And this is the important part. Settlement is not sufficient. Settlement is sufficient if the parties already know who they are, what they want, and with whom to coordinate. But many apps actually need infrastructure for counterparty discovery, because generally speaking, most individuals don't innately know with whom they should be trading Bitcoin. You need to have some sort of way to discover which counterparties you can trade with, you can settle with. And also you need help agreeing with those counterparties on exactly what you want to settle. This is true for marketplaces where you have buyers and sellers. This is true for quadratic public goods funding, where you have actually many more parties involved, where you have projects, donors, and funders. This is true for DAOs. This is also true for rollups, right? When you actually think what a rollup does is a user signs a message, they send it to a central server, that central server does some compute, and then that compute gets settled on some underlying programmable settlement system. This is true for Optimism, this is true for Starknet, and currently everyone builds this as completely isolated stacks, as in the intents that people sign for Optimism or the intents that people sign for OpenSea or Starknet aren't composable anymore. They're application specific and they're centralized. Right, so what are actually contemporary approaches to counterparties, to this problem of counterparty discovery? Well, you can do an AMM. In the AMM world, the Uniswap contract on Ethereum becomes the central counterparty discovery point. You can also do an on-chain order book. All these approaches are expensive because you're spending gas to get a globally ordered set of transactions, even though you probably don't need that. And they're kind of silly because you're fundamentally rate limited how fast you can do this because you have to settle everything in consensus. The second approach is you do the single operator centralized database. OpenSea does this, Xerox does this. Flashbots actually also does this, where a user signs a thing, they send it to the Flashbot server does some compute, and then submits it on chain. We're starting to see some more app-specific sovereign chains do this, like DYDX is a good example here. But again, the problem is this is a lot of work, and there's still trade-offs where now you just have a slightly faster consensus. You still don't have the right abstraction, because what you actually want to express is that people don't have transactions, they have intents. And intents are partial in nature, right? Like, I don't have all the state to craft a full state transition. I have like the intent that I have a Bitcoin and I want some ETH and 0 Bitcoin. That's an intent, and I need some counterparty discovery. And this is like true for most things that blockchains are currently used for. This is true for all of trading. This is true for all of voting effectively. This is true for auctions. Right, so with this, I want to talk about the third generation of protocols, which is Anoma in my mind. Anoma is a unified architecture for full-stack decentralized applications. And now that I've sort of gone over the history here, I think you can start to get what I mean. So, Anoma it's an architecture for intent-centric privacy. It's an intent-centric privacy-preserving protocol for decentralized counterparty discovery, solving, and atomic multi-chain settlement. I won't talk too much about the atomic multi-chain settlement. Isaac gave a talk earlier about how you can use Typhon to use Chimera chains to get on-demand sharding. If you're interested in that kind of stuff, check it out. It allows you to do very cool things like have atomic settlement between two sovereign chains. So the best example I can always come up with is imagine that the New York Stock Exchange is one decentralized blockchain and the London Stock Exchange is another. And with atomic multi-chain settlement, you can do like a conditional $100 billion trade on both exchanges at the same time. But today, I really want to focus on the first part, which is intent-centric, intent centricity, and counterparty discovery and solving. So, Anoma follows two key design principles. The first one is intent centricity, and the second one is homogeneous architectures, heterogeneous security. So, what does intent centricity mean? It means that users express what they want and not how to get it. And sort of the easiest way to think about this right now is that when a user, authorizes a transaction in Ethereum, they don't authorize a specific state change. They don't authorize what they want. They authorize a virtual machine to run some compute to maybe get them what they want. But effectively, a transaction on Ethereum authorizes a execution trace. And users have to reason through the entire execution trace to understand what it actually results in. This is the reason why you can have exploits using proxy contracts, because if you end up calling a broken contract, or you have a broken contract has somewhat the ability to inject itself into your execution trace, you end up in a scenario where that contract can make arbitrary state changes to your account. Because as a user, you never authorized exactly what state change you're okay with. You authorized which execution trace to take. And so intents are really binding programmatic commitments to state preferences. The simplest example is that you can say that you currently have 1 Bitcoin and you're willing to have 0 Bitcoin if you have 100 ETH. Right? This is sort of a very trivial limit order, but you express exactly what state you want to end up with rather than expressing how to compute your resulting state. And intents are fully programmatic, as in they're just arbitrary code and state. They are not limited to specific order formats. When you think of something like 0x or OpenSea, there's like a specific format, and you can only express that specific intent. In the Anoma architecture, intents are, you can kind of think of them as they're evaluated at runtime. So it's just arbitrary code that runs in order to verify whether your state changes have been met. There's also an intent gossip network that is not consensus critical, as in different participants in the network can have different views of the state of the network. This way you can have 100 million intents floating around the system. Different participants in the network can subscribe to different intents, as in like topic-based subscriptions, where maybe someone is only interested in trading large sizes of Bitcoin orders. Maybe some other people are only interested in the private second price auctions. And I mean, I'm not talking about the economics here, but there can also be economic incentives to keep gossiping intents that prevent liquidity from being broken apart. Because if you don't have this, you often end up in a scenario where different gossip nodes don't want to gossip onwards the intents because they think they sort of benefit from hoarding it all for themselves. Then you have solvers. And solvers look at 100 million intents, or a subset of them, and try to find compatible intents. For example, in this Bitcoin ETH example, this can be that someone has exactly the inverse. So if your intent is that you are willing to sell 1 Bitcoin against 100 ETH, and someone has the exact inverse, that they are willing to sell 100 ETH against 1 Bitcoin, those would be compatible. And then a solver would look at this and go, oh, these two intents are compatible. Let me create a transaction and submit it. But this can also be that you have 100 intents that together form a valid transaction, where maybe you have 100 individual counterparties that are willing to trade a portion of a Bitcoin for some ETH, right? And this is the very important thing. Intents are composable, as in different applications will have different intents, but as a solver, you can reason through all of them. And so instead of having a specific intent that just works with OpenSea, you can have intents that work with OpenSea and also 0x. And when solvers look at this, they can take all these kind of different intents and compose them and settle them on chain. And yeah, then transactions are settled on the settlement layer. On the solver part, this is most likely an NP-hard problem to build a generalized solver. So most likely as a solver, you should pick some subset that you want to optimize for, whether this be fungible token trading or like the voting intents or the like NFT intents. And this kind of architecture is necessary to enable decentralized counterparty discovery. And this is what the majority of mainstream dApps are starting to realize, because everyone is trying to build this kind of counterparty discovery service, except that everyone currently builds this as a centralized Web 2 server that is completely non-composable with what everyone else is doing. And this leads to this declarative paradigm for dApps, where instead of authorizing execution traces of how smart contracts are allowed to change your state, you authorize the state changes first, and then the system can figure out what is the best way for the system to get you to your desired end state. As a result, you get a very nice black box architecture from a user side. A user only has to author and submit an intent. Then magic happens, where the system figures out how to best satisfy the sort of desired state changes in a user intent, tries to optimize that as many people get settled as possible, and afterwards, users just need to check that the state has been updated, that their intent was actually settled on chain. which coincidentally is, I think, what most people have as a mental model for when they interact with blockchains. I think when someone trades on Uniswap some ETH for DAI, they don't think that they are authorizing an entire smart contract call stack to do arbitrary things and that they need to verify what every single instruction does. The mental model that people have is they're trading like some state, some DAI for ETH, right? But Anoma really, or an intent-centric architecture like Anoma, allows for the intuition that people have to match the reality what's happening in the system. So I won't go through the entire thing. This is sort of the overarching architecture of Anoma. I'll very briefly run through this. I'll skip over a bunch of the privacy stuff. There are different talks. We had a talk 2 days ago, about Tiger as the unified execution environment, so this should be online as well. And Chris will give a talk at ZCon, if anyone here is going to ZCon, about the unified execution environment. So the first component is this box on the left, which is decentralized counterparty discovery. Here, users can write intents that could be transparent, shielded, or private. As a result, intents include the desired state changes. Maybe they include some zero-knowledge proofs as well. Those intents are then submitted to intent gossip nodes. Intent gossip nodes gossip these intents around. There can be, again, an arbitrary number. This is not limited as in consensus-critical messages that need to be globally ordered. There can be 100 billion of them, and if you don't want to see some of them, you can just not subscribe to that specific intent or that specific topic or that specific class of intent. Solvers look at the subset of intents that they're interested in. If you are very good at building NP-hard algorithms, you can probably write a generalized solver, and you then could look at all intents and try to find optimal computational results. But generally, solvers will look at a subset of intents. Once they found a set of composable intents, and this could, for example, be that I am willing to trade ETH for Bitcoin, someone else is willing to trade Bitcoin for atoms, and the third person is willing to trade atoms for ETH or Bitcoin, whatever completes the cycle. Those three intents would be composable. A solver can take them, combine them into a transaction. The important thing here is, at that point, solver, before someone submits a transaction, they encrypt it against the public key of the system. We are using Furrier here as our distributed key generation protocol. It's a shared public key that is controlled by the validator set that allows us to only have encrypted transactions in the mempool. As a result, none of the transactions are front-runnable because they are hidden from sort of the general view. Then, now we come into this consensus box. So the transaction mempool only contains encrypted transactions. Validators take these encrypted transactions, they put them into blocks. They can't inject their own trades into this. They can't front-run, back-run, or sandwich people here. Proposers propose blocks of encrypted transactions. In the next block, the validator set jointly starts decrypting those transactions, but the ordering is already fixed, so they, again, can't front-run you there anymore. The way this actually works is this requires ABCI++ in order to get something called vote extensions to make the entire decryption step happening. This is why we are very interested in implementing ABCI++ in Tendermint Core. Right, now we have a finalized block. All transactions are decrypted. Oh, the decryption step also follows the same BFT threshold, so any 2/3 of the validator set can decrypt, which means that no individual validator can decrypt those transactions either. Yeah, and then we go to the execution environment, and here the interesting thing is this execution environment can actually be on many different systems. This could be on, you could like use Ethereum as an execution environment, you can use Anoma as an execution environment. This is sort of, I'm coming to this in a sec with regards to homogeneous architectures, heterogeneous security. Right, homogeneous architecture, heterogeneous security. Protocols benefit massively from everyone agreeing on the same protocol. This is why IBC is great, for example, because if we all agree on the same interoperability standard, we can just use the same underlying protocols. And this is actually fine because everyone wins just by agreeing on the same protocol. Even if you could write a slightly better implementations, the losses you're taking on are marginal in this case. Homogeneous architectures are what makes phones great, because my phone that I bought in Europe works in North America and it works in Asia because we've agreed on the cellular backbone protocol, and there's a homogeneous protocol, and my phone can just roam between these different systems. However, security domains aren't benevolent monopolies. They can charge you rent, they can steal your money. Different people may have different requirements for what they would consider secure. For example, some of us may consider that the Cosmos Hub is the most secure security zone, and we want to have all our security to be derived from the Cosmos Hub. A bunch of other people earlier this week, probably consider Ethereum to be the most secure settlement layer, and they want to have all their security derived from Ethereum. I would probably argue that most people in the real world care about their local communities being able to control their security. I think my parents would feel much more comfortable if their local city guarantees them their security for their financial transactions and their blockchains. The important point is not that we need to pick. The important point is, as long as we agree on protocols, every user can pick their own security model. And they can decide to opt into either a global Cosmos Hub or Ethereum security model, or they can opt into a local security model. We get a lot of benefits from separating protocols and architectures from their security model. As a result, with the Anoma architecture, you get different deployment patterns. You can deploy this as a sovereign L1, you can deploy this as a community-operated chain by your local village in Switzerland. You can deploy this as an L1.5 if you just want to decentralize a specific dApp or L2 on Ethereum, where you just use the intent, gossip, and solving part. You can deploy this as an L2, where all of the security is derived from a different blockchain. The L2 deployment would most likely be the shared security deployment with the Cosmos Hub. Yep. So then, in the first case, you only use the intent gossip network and you sequence and settle elsewhere. In the second case, you use Anoma to decentralize not only the intent gossip, but also the solving. Or you can use it to decentralize specific dApps. And the last example is sort of everyone deploys this as their own sovereign L1. Right, dApps on Anoma. So what components do they actually have? They have intent formats which describe what users actually submit, and there will be some standards, but they're not encoded in the protocol on how do you form these intents so that solvers can easily figure out and look at many different intents to be able to compute over them. There are solver algorithms which take specific intents and try to find optimal solutions for them. And then there are validity predicates which enforce settlement invariance. For example, for bridged assets, you have the invariant that if you have a bridged an asset, the system you're currently on can't create extra of these assets. So, for example, if you're sending Bitcoin around, your settlement invariant is that the transaction can't create or destroy Bitcoin. It can just make sure that it moves from different accounts to other people. And this kind of vertical integrated architecture means that you get end-to-end security guarantees, liveness and privacy guarantees. And the really cool thing is that you don't get vendor lock-in, because you can take your applications and roam across different security domains, which is what happens in the real world at the moment. Like when I fly to the States, my phone now roams from my European security domain into the North American security domain. This is incredibly convenient. This is also kind of how passports work. People roam from different security guarantees, security domains, but with a homogeneous architecture. Okay, oh wow, 2 minutes. Right, what can you build with Anoma? So these are examples of existing dApps that you can build, but with full stack decentralization. You can use Anoma or the Anoma architecture to decentralize things like 0x and CowSwap, to decentralize OpenSea, or to build very capital efficient AMMs. You can also use them to decentralize rollups or things like public goods funding, which I think the people in the back will have a hard time seeing. It's at the bottom here. Generally speaking, Anoma generalizes this architecture which everyone has, which is you need decentralized counterparty discovery, solving, as well as programmable settlement. But just as I mentioned in the beginning, when we went from Bitcoin to Ethereum, later on we realized that there are a bunch of novel applications that we can probably build on top of Ethereum that we didn't even think of when we upgraded from Ethereum to Bitcoin. And in the same sense, I expect that there will be a lot of novel applications that people come up with over time that can be built on Anoma that we aren't currently even thinking about. One of those things is something like private DAOs, where the votes are private, but the results are transparent. The other one is private auctions. You actually need Fervia for this for programmable threshold decryption, where you keep all bits private until You have all the bits in, and then you do the revelation all at the same time without new bits being able to be submitted. This is how you implement trustless second price auctions. You can build something like private games. I think the thing I'm most excited about is multi-party, multivariate private bartering. The idea that we don't really need to have base money anymore if we can just all barter directly with each other, and we can have 100 million intents, and all these intents are composable against each other, so you can take 100 million intents and everyone gets what they want if they net out in the end. Oh, and you can have on-demand or runtime rollups, because what is a rollup effectively? A rollup is a netting out of state changes. So if I have an intent and someone else has an intent and a third person has an intent, and this only results in a tiny state change on the underlying system, you can just run these as, like, intents just compose as runtime rollups. For now, this is like very different because no one has intents and everyone builds these like very specific applications. But once you generalize this pattern, you just get these kinds of things. Anoma is built by Helix, a team at Helix. If you want to check it out, we have t-shirts upstairs, and I think there is a non-public version of the white paper still there. So if you want to find the white paper, check that out as well. Anoma, a unified architecture for full stack decentralization. Thank you very much.